Hi, Saham. Hi, Dipman.
Hello.
Anybody else coming in? So, any doubts from yesterday?
No, it's clear.
Sorry, I couldn't see who spoke.
Sorry, ma'am.
Okay, Dipman spoke. Saham, can you speak once? Anything. I just want to register your voice in my head. You understood the yesterday's lecture?
Yes, ma'am. The book it's written that if we integrate the other function, get y plus dy to the power. Can you understand how that?
Your voice is not coming clearly, Saham. Hmm?
Uh, am I audible?
Yeah, better.
Uh, in the book, uh, when the generating function with respect to the other b, I think it was b, okay, then oh sorry, uh, it shows that a and y is equal to 5 times 1 plus dy a n minus 5. I don't understand why that.
Where exactly are you speaking?
Pardon, ma'am.
Let me open my copy of the book. Which page you are referring to?
Ma'am, page 22.
Page 22. What here?
Uh, ma'am, second last paragraph.
Second last line. Second last word.
It turns out that the sequence increases for a while and then it decreases. That is, it has just one maximum. Many combinatorial sequences are unimodal, like this. How are they proving the sequence use form?
And sequence.
Hmm?
So anyway, we haven't really, you know, in the detail, we haven't read the unimodality of the sequences. So maybe let's just wait till that topic comes up because that will be covered later. Just that is what is going on. So, either my internet is weak or yours is not fine. Ridiman, are you able to hear someone clearly?
No, I can't hear Sam properly, but I can hear you properly.
So, Sanam, can you try moving to some more open area where you get a better network connectivity?
Uh, well, I don't think I can get better connectivity than
No,
this.
now it's good for
Yeah,
Sanam. I can
now
hear him.
it's audible.
Okay, I think it may have to do. So,
Or maybe you just need to speak a little louder. Just to
yes,
hear you.
I think the mic was far away from my mouth. So,
Yeah. Okay, so if the doubt is that you don't understand what human modality is and how to really see from the function or rather the sequence, how it's increasing or decreasing, let's just wait till that topic comes in the full force, or the doubt is something else.
no, my question was how they from that from.
Okay,
Yes,
that we will see later.
yes,
We'll learn that slowly. Okay,
yes, ma'am.
so yesterday we stopped at the point where we figured out what we would choose as a generating function for Bell numbers, right? So just a little bit of more theories left there, and then we will shift to a new chapter. I'll go slow today so that you have more time to sort of absorb this data. Oh, you don't see initial experience. Is my screen visible?
Yes, ma'am. So, in last time, this is what we said that this is the generating function which we are going to choose for my Bell numbers. Okay. So this is the exponential function. Okay. Now, so to deal with things like this, or maybe there was there is an exercise maybe which will show up in the assignment sheet, of course, is that find the which means you have to like literally compute it. Okay. And now I'll tell you the answer also. Dx turns out to be e raised to x minus fine. So this is the answer which you will figure out later through your assignments, but I am going to start from here for today. So Remember bx I have said is this. So what we get is this is equal to bx to e raised to x. Now, can anyone suggest me how to really solve this? Tackle such problems. Involve exponential functions. Hmm. So for this, what we have this operation, the x ddx log operation. So what we do, we take the log on both the sides. So if we have something like this, we take the log here, we take the log here, then we differentiate it. Taking log will remove this base exponential here, right? Everyone knows this? Yes, people.
Yes, yes, ma'am.
So we take the log just to get rid of this exponential term. Then we do the differentiation because differentiation anyway does not lead any change on the exponential terms. So the rest of the terms, whatever unnecessary things are there, will be eliminated and only the rest of the things will be left. And then to multiply by x because here you would have reduced the power of x because of the differentiation, right? So that is the method I am listing here, like taken from the book as it is. Take the logarithm of both sides of the equation, differentiate both sides and multiply throughout by x. Here the equation of fractions, and then for each n you have to find the coefficient of xn on both the sides, and then obviously you compare them to get the value, right? Now on this, let's try to apply this method. So when we apply this, step 1 would be right? So I will be left with what? Yeah, please start dictating. But half the things are not coming. Oops. Here it's in factorial, and here I will be left with just e raised to x minus 1. Correct? Step 2 tells me that you have to do a differentiation. So differentiation of a log term is what? F x over fx. Correct?
Yes.
See, we do not have so many participants, so it's okay for you to keep yourself unmuted because I understand by the time you figure out how to unmute yourself, it takes up some time and then we are not able to interact with each other. Okay, there are just three of you. So keep yourself unmuted and then we can literally talk how we would have done if we were in a classroom. Okay,
Okay.
so when you do the differentiation on this term, you're going to have summation being n xn minus 1 over n factorial and that converted to a summation being xn multiplied this be equal to raised to x, right?
Yes.
Further manipulation is going to happen. That's summation bn n being xn minus 1 over n factorial is raised to x expansion, sorry, x expansion. Technically, I am not applied this, so it's hard for me to read this as a summation. Yeah, so this is clear. You can see the coefficient of x raised to n here, right? It is n plus 1 bn plus 1 over n plus 1 factorial. That's going to be the coefficient of x raised to n. But here now you have a product of two sequences. So what would you do? See, here it is easy to see the x raised to n. This is however product of the particles. Okay, so you will have to use a Cauchy product and then figure out the term which is the coefficient for x raised to n. Right?
Yes.
I need quick responses. So that is what you will do and figure out what turns out to be the answer. Okay?
Okay.
Next, oh, we skipped something altogether. That's why. Fine. Let's step 3 also, which was to multiply by x. So we're going to get this into x. So this particular thing would vanish. And here we
Yes.
get an x. So this is what you have to find out. So, right? Okay. So you will
Yes.
solve this. Use a quotient product, figure out the coefficient of x raised to n in this entire thing. Figure out the coefficient of x raised to n here, which is clear, n bn over n factorial. Bn you already know, we completed in the last lecture. And then equate them. Those are going to be the end of it, which is the last step, step 4. From Q,
So let's use it. Besides.
Yes.
With this topic ends. You are going to do this exercise.
Okay.
Now, so far we have been seeing all these coefficients and sequences. Now let's just little more professionally towards the formal power series. I'm sure all of you have already seen this material, but for the sake of completeness, let's just go through this. So now we are really shifting to what is chapter 2, which is important. So far, like I think in the last lecture or the one before that, we were talking about series and then more if we can work with them. Such questions, of course, are very naturally to arise when you're working with series, right?
Ma'am, your voice is breaking a bit. I think, I don't know, it might be a problem from my end also. I
I
couldn't
couldn't
hear
hear it.
what is.
I couldn't hear as well.
Okay.
Okay, so now we are shifting to formal power series.
Okay. Yeah.
Is it better now?
Yes. Yes. Yes.
Maybe I started speaking very slowly.
Okay.
So, what really happens is that when we are dealing with power series, we might be worried that maybe the series which I'm working with, maybe they converge, they don't converge, and whatever we are doing, whatever hard work is going on in the computations, manipulations, etc., if that is even worth or not. Because if at all, if in the end it does not converge, what use is it of, right? So this
Yes.
chapter is all about taking that guilt away from the mind that doesn't matter. The power series which we deal here with, they actually are worth working with because the formal power series they form a ring. So when you take the product, etc., they stay in a well-defined range and then you can work with them. And that is another reason why I have left this with you,
Product of two power series.
product of two power series. Okay, so this is the main data now. This is the main objective now to see why we can work with these formal power series without really worrying about them. Okay,
Okay.
so just for a sake of definition, formal power series has the form 0 plus e1x plus e2x square and so on. Okay, and these terms a0, a1, a2 and so on, this when you see this is called the sequence of coefficients.
Okay.
Well, so very basic things like if you're dealing with some power series, let's say formal power series fx, so someone's phone. Okay, this is not the reason why I asked you guys to keep yourself unmuted. It's
Oh, no, sorry, ma'am. It was.
keep yourself your phones on
Hmm.
mute. Okay, so whenever I say fx, unless I'm saying it otherwise, this is the notation I am following in my head. Okay,
Okay.
So the coefficients for fx are really the f0, f1, f2 and so on. So what would you tell me if I write gx? Just look at it. Oops.
G1.
Plus x square and so on. So two formal power series are equal or same, that is some fx is equal to gx if and only if
All the coefficients are equal.
component wise all the coefficients are same. Yeah, if each of these coefficients match the corresponding coefficients, then we say that the corresponding formal power series are same,
Equal.
equal or same. Further, if with the same thing I tell you that I am working with some fi, xi, sum over I, and I do a plus with gj, xj, summing over j, what will this be? Yeah. Simplify it.
Fi, yeah, fk plus gk x to the power k.
Why put the bracket in the correct place? Okay, and similarly, if I do this, subtraction here. Okay,
Yes.
so this is how I do addition option of the formal power series. So this is getting too much. Let me just reduce this to FES, formal power series. Huh?
Okay.
So once you have the addition and subtraction, what next can you think of?
Multiplication.
Multiplication. Great. So how will that look like? We have fi xi is corrected with gj xj is the ck x. Now everyone who's aware of the ck, and these two is equal to k. Fi gj is equal to
No, x raised to k is already,
oh,
I
that
mean,
is
c.
outside. Yeah,
Yes,
yeah.
yes.
Nice, nice, nice. Okay, is this fine? So you sum over all those indices that add up to give me the value k. You collect the corresponding fi terms, you collect the corresponding jj terms, and take their product and take all such terms. And their summand is what is my ct. Right?
Yes.
this. So just like this, you know it's process form. This. This.
Okay.
What more can you think of?
Division is, I mean, 1 by
Yes,
of
something
power
like a
series.
reciprocal.
Yes, yes.
Okay. So yeah, fine. So now reciprocal of a formal power series. Suppose fx is a formal power series that I am given with. What does it really mean to say reciprocal of fx?
1 by fx.
1 by fx, or rather if some other function is there instead, then reciprocal of fx is a formal power series gx such that
Fx times gx is equal to 1.
great. Everyone agrees? Now we know how to multiply two power series.
Yes.
So just try to evaluate this time. Fx gx is equal to 1. So fx looks like f naught plus f naught plus f x square and so on times 3 naught plus 3 1x plus 3 2x square and so on. This entire thing has to be 1.
1.
1 is a coefficient of what power of x here?
0.
X equals to 0. So can somebody tell me the terms which I'm going to get out of this product, which is the
F0 G0.
F0 G0, which means F0 G0 is equal to 1, right?
Yes.
This implies this. So
Hmm.
in particular, F0 can't be 0
Right.
and same is true here. Okay, fine. If
Yes.
any one of these becomes 0, then the product can't be non-zero. As simple as that. So with this, we have a proposition
And this is that the formal power series effects, which we write as this, as a reciprocal if and only if F0 is non-zero. Okay.
Yes.
Furthermore, the reciprocal of F is unique. Very important part. So this we have already done, right? This part is already done, right? We have seen this. If this has a reciprocal, then we have a function power formal power series G, and then you can take this product, and since you're saying this has a reciprocal and this is a reciprocal, this is a reciprocal, the product has to be 1, and then you reduce this entire thing and come down to the fact that F0 is not 0. Well, why should the reciprocal of F be unique? First part already done. Second part, any ideas? What can you deduce from here?
If we suppose there are two reciprocals, G and G prime, then G0 should be equal to G prime 0 because both of them should be 1 by F0.
Fine.
And about the other terms also, uh, using that product, uh, I mean all the other the coefficient of ax and x square and all those should be 0. So if we use that Cauchy product thing we did, then also I think we will be getting that they are equal.
You think? Let's just do it
Uh,
for the smallest possible case, and rest you can figure out at home. Okay?
okay.
So if you look at the coefficient of x raised to 1 in fx dx, what are the terms really?
F0 G1 and F1 G0.
So this tells me that f0 g1 plus f1 g0 should be equal to,
0. Yes.
correct? But I know
Right.
f0 already. G1 then turns out to be minus of f1 g0 over f0.
Yes.
So G already Ridhiman has told us that G0 is determined. Okay. F0, F1 I already know they are determined. This is part of the series that I started with. So I know the values of F0 and F1. Further, I also know that F0 is non-zero. So it can be put in denominator, and this makes G1 determined. Right? So far we have G0. So G0 and G1 are uniquely determined. Right? If you go for the
Yes.
if you go for coefficient of x raised to 2, what all I have? F0 G1, sorry, G2 plus F1 G1
F1 G1
plus F2 G0. And this
G0
equates to
0.
0. So again I have the same thing. G2 turns out to be minus of F1 G1 plus F2 G0 divided by F0. Correct?
Yes.
All of the things that appear on the right hand side of my equation are they determined?
Yes.
So this determines my G2 also.
Yes.
G2
We
is
can prove using induction like this.
right. This way, each of these is actually and hence the formal power series. Okay, done. So this was about the reciprocal of a series. Can you think about something like the inverse of a series? So reciprocal is something which you know, when you take the product, you get the unit element. But inverse is something that the product does not make any change to the input variable. So f of g of x becomes x. G of f of x becomes x. Can you think something of that sort for power series?
I mean, in place of x everywhere, we will have to put gx then, and
So think about it. I'll just be back. Give me 2 minutes.
okay.
Think about this. Whatever are your intuitions, write it down and I'll come back.
Are people there or everyone left?
I'm here.
So what a inverse of a formal power series would be, according to your intuition?
You can substitute like x to g inverse of x in the
What is G inverse of X is what we're
like
trying to figure out.
like if your power series is like g of x equals g naught plus g1x and so on,
Mhm.
then put like instead of x, replace x with g inverse of x, so that on the left side you have like x because g of g inverse is x, and
Yeah,
then
but G inverse
right
is what is not known to us as of now.
yeah, that's how you'll compute it. On the right you'll have an infinite polynomial in g of x. Oh, sorry, in g inverse of x, and then you can assume coefficients for g inverse of x, and you'll have like
Okay,
multiple.
so to
Yeah.
cut it short, sorry if you just interrupt in between. What he is trying to suggest to us is that if you start with Gx to be G naught plus G1x plus G2x square and so on, in places of x, you put G inverse of x, right?
Yep.
So instead of calling it G inverse, let's just call it as fx.
Okay.
Because anyway, we don't know what G inverse is.
Right.
So once f has been found, then we can say, okay, this f is the G inverse. Okay, so
Yep.
inverse is a formal power series fx such that g of f of x, or you take f of g of x, they equate to x, right? But these terms
Yes.
you have to make sense of, right?
And why will it be inverse on sides?
Sorry.
I mean, it could happen that g of f of x is equal to x, but f of g of x not equal.
No, so we are talking about D inverse. So it is a two-sided inverse. And anyway, like we are into the arithmetic which is all commutative, no? So we demand both these conditions together. G of f of x should be same as x, and so should f of g of x be. But then question is, what do they really represent?
But it's not necessary that functions are commutative.
It's not necessary, but we demand both of these conditions to be true at the same time. Otherwise, we would have to talk about left-handed inverse, right-handed inverse, and all, right? We are talking about the inverse. So left and right hand inverse, we would want to be the same. They should coincide with each other. So to put down in the records, f of g of x, first of all, let's just say if f of x was f naught plus f1x plus f2x square and so on, the f of g of x is really f naught plus f1 g of x plus f2 g of x whole square and so on, as Rishivesh has already guessed. So in shorthand, this really looks like f of I, f of n, g of x raised to. This is what f of x is. Okay.
And similarly, you can see what g of f of x would be. Here, instead of fx, you would instead of x, you will have an fx. Instead of x square, you will have f of x whole square. Instead of x cube, you will have f of x whole cube, and so on. Now, in this term, so this, if you really expand further, this would have been f of not f naught plus f1 gx as a series is g naught plus g1x plus g2x square and so on plus f2 g naught plus g1x plus g2x square and so on. All this also square and so on. You see so much so on is going on. So if g0 is 0, what can you see?
The coefficient of x in the whole thing should be 1 and all the other coefficients need to be 0.
Yeah.
And the coefficient of x appears only in the term, I think, f1g1.
Right. So
I don't think it
yes,
appears only in F1G1. It will
basically,
appear in the square also, and probably in the cube and all that. You get infinite equations.
In the square, yeah, right. It will
okay,
also
let
appear
me
in
let
the.
me put it out other way. What happens if g0 is 0? Then does every term of this series f of g of x contributes to each power of x?
Yes.
If g0 is 0. So if g0 is 0, then for the terms that have or at least, okay, let's just see this. So if g0 turns out to be 0, what is the coefficient of x raised to 0 in f of g of x?
F naught.
S naught. If g naught is non-zero, then what is the coefficient of x raised to 0?
Then it's really big. I mean,
Very
it's an infinite thing.
correct.
f naught plus f1 g naught plus f2 g naught squared.
And so on. So
Yeah.
this is what I'm really trying to pinpoint. Hey guys, second warning. Huh? Keep your phones on silent. So suppose g0 is 0, then coefficient of x raised to 0 in my f of g of, okay Rishikesh, since you are new, this just means this particular bracket in the square bracket and x raised to whatever power of this, whatever function appears here, says that coefficient of this particular power of x in this series. Okay,
Yes. Yeah.
so this, as you've already told me, turns out to be f0,
Right.
right? And even for the power 1, things are a little better to see. x raised to 1 comes from here.
F1 G1.
Will it come from here?
No,
Why?
because if we take x common from the whole thing, the square becomes x squared. So each term will have a x squared tagged along with it.
What are you saying? What is a plus b whole square?
X squared plus 2ab plus b squared.
So a plus bx whole square would be
A squared plus 2abx plus b squared x squared.
so 2abx.
No, but we are considering g0 to be 0, right?
Right.
So I mean, we can take a x common from all the terms, because all the terms have
Correct,
a
correct.
x.
Yeah.
And then if
That-
we square it, it becomes x squared.
If
That's what I was saying.
vanishes here, the lowest power survives inside this bracket. Lowest power of x is 1. And that
Yes.
when squared is already x squared. So you have nothing
Yes,
from
yes.
here, only thing from here. And that is f1 g1. Fine. So this turns out to be f1 g1. So you see, no term from this bracket or any further bracket is going to contribute to this. Correct?
Yes.
And similarly, same thing happened here. Since G0 was 0, nothing from here or here contributed to this. Right? So, in such a case, computing coefficient of x raised to n in this is a finite term. Right? You would exactly know what all is going to appear. Is that right? Yes, please speak. Oh, that is my stylus settings. Okay, so computing these things is nice. Fine. However, if G0 was not 0, then every term from here would possibly, depending on if let's say G1 turns out to be 0, then this thing would vanish in some cases. But if G0 is non-zero, every term of this entire big summand may contribute to each power of x raised to n. Each power of x. Is that right?
Right.
So in such a case, most of the coefficients of x raised to n is actually an infinite sum. Okay?
Yes. Okay.
So,
But ma'am, we are looking for a function which is the inverse of f. So we can set the g in any way we like, right? So we can choose g not to be 0 if that gives a
that would really depend on the function f. No, you do not. You
okay,
can't
okay,
choose
yeah.
yourself. All this analysis is being done on the composition of these power series. We are not saying that, oh, if something like this happens, then this is possibly a better candidate for the inverse of f or not a better candidate. That is not the debate. Debate here is that once we talk about the inverse of the formal power series, then from that composition power series, what you have, what can you extract? Depending
Okay,
on
okay, yeah.
some terms being zero or non-zero, how nicer or how huge monstrous it can be. Because ultimately, if you have not forgotten, we are into the course of generating functions, right? So all the time
Yes.
we would be interested in finding the coefficients of x raised to n. So in particular, there may be cases when we when we hit upon something like composition of two power series.
Okay.
So like, see, to do all this analysis, I am not using the fact that this turns out to be equal to 1 or x, anything like that, nothing. This is just the definition for the composition, and from that we are doing the further analysis,
Okay, okay, yeah.
right?
Right.
So this analysis has got nothing to do with the inverse. This analysis is
Okay,
about the composition of the power series.
okay, okay.
And since this is what we would ultimately be interested in, that is why we are trying to see when things of this form would be nicer to evaluate and when not. Yeah?
Yes.
Okay, great. So this is being said, let's come to a different proposition. Okay. It states that if fx and gx are two formal power series, that so this ST, I think it's quite standard among everyone almost. This is such that is that f of g of x is equal to x and same as g of f of x, which means they are inverses of each other. Then f of 0 is equal to 0 is equal to g of 0, and f1 can't be 0, so can't g1 be. Can someone see a quick proof of this, at least for this part?
Yes.
Yes, please. Hmm?
I mean, for the equal to 0 thing, we just saw it how uh, taking the composition gives. Uh,
Correct, just put that formula.
yes.
So f of g of x is equal to this, right? And this we say is equal to x.
Yes.
Yeah. So what powers of x really, what is the coefficient of x raised to 0? So
F0
coefficient of x
and
raised to 0. compare these two, and you're going to get that F0
F1
plus
G0.
plus F1 G0 plus F2 G0 square and so on, which is equal to 0. Is that right?
Yes.
Taking the G0 common, we have F1 is comparison to the 0. And when you equate the other way around, you are going to get the equation G0 plus G1 F0 plus G2 F0 squared and so on to be equal to 0. Correct?
Yes.
So if you like, you can equate these two to each other, and then F1 G0, G1 F0 and F0 G0, you collect them together and see that if any one of them survives, then this summand can't be 0. Okay? Following me?
Okay.
So, now in this ring of formal power series that we have seen, there are some other operations also that we have. So, I mean, we have already seen subtraction and addition. We have also seen the product. We now know about the inverse and the reverse, or that is reciprocal. We now see the derivative of a formal power series. So I think as soon as I leave it to you, you would start shouting, man, this is going to be this. So putting it down for records. Okay, guys, you don't have an issue if I stretch the lecture for like 10-15 minutes extra?
No,
10
it's fine by
minutes.
me.
Oh,
Maybe we'll I'll start taking 3 times a day. You guys are aware, no? We have a shortened semester this time, but the course syllabus is not shortened, so we have to cover it somehow. Is it okay? Other two haven't given me a nod.
yeah, I don't have a problem. My other courses aren't very heavy in the first semester.
I might have a problem. I
Well, I think I would prefer instead of meeting 3 days, if we could meet 2 days and stretch it longer, that will be, I guess, better for me at least.
Yeah, that works better even from a teaching point of view, because meeting 3 times means, recapping the things 3 times, and recapping
Yes.
takes quite a lot of time.
Yes.
Okay, so we'll meet twice, but maybe for 1.5 hours or 1 hour 35 minutes, whatever works out.
Okay.
And next week we'll meet as scheduled, but week after that there will be some changes. I'll let you know on the Monday
Okay.
of that week. So I'll let
Okay.
you know on 11th of October. Fine.
Okay.
So let's come to the topic of
derivative of the formal power series. Okay. So if you have a power series fx to the summation en x raised to n summing over n, the derivative f dash x or f prime x is going to be the power series which looks like this. Okay.
Hmm.
This is the derivative of. Now quickly two results. So proposition first part is if f dash of x is equal to 0, then f of x is a naught, a constant. And second part is if f dash of x is equal to f of x, then f of x is some c exponential x. So everyone remembers this? Can I scroll down?
Yes.
Oops. So to see the proof, it's quite easy, for at least for the first part, right? F prime x is equal to 0 as a power series means that its summation n en xn minus 1, this is 0. Yeah. So comparing the
Yes.
coefficient of x raised to 0, you have this to be 0. Correct?
Yes.
Only the last term survives. So let me say coefficient of x raised to n in my f dash x is 0 for all n. Correct?
Yes.
This is same as saying that coefficient of x raised to n in f of x is 0 for all n bigger than equal to 1. Is that correct? This summation starts from
Yes. Yes.
and this is 0. So x raised to 0 is also 0 here, right? So that means f of x is equal to a naught plus 0 times x plus 0 times x squared and so on. So it turns out to be a naught, which is a constant. Fine.
Yes.
And for the second part, f prime of x to be equal to f of x. Well, what does this really tell me? What was the definition for the equality of two power series?
Each of the coefficients will be component wise equal.
Right. And what is the coefficient of x raised to n in this? So this
In
tells
fx
me
or
that
f dash x.
in both, this should be equal to this,
Yes.
right? What is the coefficient of x raised to n? At least here you tell me first. X raised to n in fx is? See f, oh, didn't I write in here? Huh.
So f is
Fn.
summation an xn. Oh, I'm so sorry. I had been writing fn, no? Okay, let's just see it as an here. So fx is summation an x raised to n. So what is the coefficient of x raised to n here?
An.
An. Coefficient of x raised to n here would be
An plus 1.
times n plus 1.
Yes.
So that's what we write. So this is an and this is n plus 1 times an plus 1. Okay? Or an plus 1 is nothing but an over n plus 1. Correct?
Yes.
And this would be an minus 1 over n plus 1 and n. Right?
Yes.
You just keep on going down.
Hmm.
So you can use induction or otherwise substituting that. Induction hypothesis, what you really get is that n plus 1 is nothing but a naught over n factorial,
Okay.
right?
Yes.
So n plus 1 factorial started from n plus 1. Was all from 0 to 0. We are computing a n plus 1. Okay, so this tells me that f of x, now you know the values. You just keep a naught as it is, and then instead of a1, I would have put a naught over 1 factorial x plus a naught over 2 factorial x squared. Everyone following me?
Yes.
And this, when you take a naught out, what is left inside is nothing but e raised to
E to
x
the power x.
and hence proved.
Hmm.
Okay, so this
Yes.
c also is determined. This is nothing but the
A naught.
a. Great. So yeah, I end today's lecture here, and let's meet on the Wednesday.
Okay.
Guys, please keep checking Moodle. I will upload a assignment sheet
Okay.
by Sunday. Okay?
Mm-hmm.
Okay, chalo. Bye bye.
Hmm.